I'm Daniel Beverly, and I wanted to talk to you guys about how vegetation responded during the solar eclipse of 2017. The solar eclipse was a pretty iconic event across North America that sparked a lot of discussion about animal behavior responses, but there was very limited discussion about how plants respond to the solar eclipse. So the primary objective of this research was to understand how photosystem 2, or photosystem efficiency, which is a primary mechanism of photosynthesis, was impacted by the solar eclipse. And so to do this, we went outside 80 miles southeast of Yellowstone, and in the line of totality, we set up instrumentation to quantify photosynthetic parameters that would be impacted by the solar eclipse. So on the map, on the right, you can see the western United States, when the blue represents sagebrush distributions across the states. The gold band that you see is the path of totality, or the complete darkness zone from the solar eclipse, and the star denotes where we actually took measurements. So after setting up instrumentation and getting our protective eyewear situated, we went and observed the plant responses from the solar eclipse. So we have figure 1, the 3-paneled figure in the middle, and we have panel A with his net radiation on the y-axis and time on August 21st, 2017 on the x-axis. The gray bands denote the partial eclipse, and the dotted lines denote totality. And so as we entered into the partial eclipse, you see a reduction in net radiation, or the reduction of shortwave radiation, until we hit totality, which we hit our minimum with 0 incoming radiation, and then we recover as the partial eclipse subsides. Panel B, we have air temperature, and as we enter into the partial eclipse, we start to see a slight decline, and then after totality, we saw a 9-degree temperature decline with an 8-minute lag. And in panel C, we have the other driver of transpiration, which is vapor pressure deficit, and we saw the same decline with the same similar lag following totality. In figure 2, we actually see the biotic response. So on panel A, we have photon flux density, or the photosynthetically active radiation, on the x-axis, and PS2 efficiency, the driver of photosynthesis, on the x-axis, on the y-axis, sorry. And so as we progress into totality, which would be the blue, we see a linear pattern as we would typically imagine going into darkness. And as we come out of the solar eclipse with a rapid onset of radiation, we see some sort of perturbation of PS2 efficiency. So as you can see this further in this inset figure with photosynthetically active radiation on the x-axis, and the difference between the hysteresis on the y-axis. And you can see the differences are observed at the mid-range of photosynthetically active radiation, and then recovering back at high light. In panel B, we have a zoomed-in window of the solar eclipse. So we have the time where we were taking gas exchange and photosynthesis in green. We see a large decline in photosynthesis. And then on the other axis you see non-photochemical quenching, which is essentially a parameter of heat dissipation. And that's the gold. And the gold was collected from one instrument, and the black was collected from a handheld instrument during the same time points. And we can see the similar decline in the photosynthetic parameters on how they're responding to radiation inputs. On the bottom, figure 3, so we took the sagebrush area from the map on the right here, and we scaled it for simulation for a normal day, so no eclipse in the light gray, and eclipse in the dark gray is what we observed. And we saw a 27% reduction from modeled versus observed. And so for concluding facts, we saw a substantial impact of daily decrease in carbon assimilation and a photochemical perturbations in PS2 efficiency and non-photochemical quenching. Thank you.